Good morning. Another day, another chapter. Today we are looking at chapter 38. Now this is referred to as quantum mechanics or quantum physics. We had just finished chapter 37, which also was quantum mechanics or quantum physics. We're going to see that we're going to get into more detail here. This is kind of the full-blown quantum mechanics, quantum physics representation. So a bunch of topics that we're going to be looking at. Now we're not going to be able to see everything in complete detail, and so some of these slides, it's going to show things so that you guys can see kind of the foundation for quantum physics or quantum mechanics. Some items will slow down and stop. Those are the ones that you're going to be wanting to be able to do those kind of examples. And other ones we're just going to take a look at derivations of formulas and where they're coming from. So this is quantum mechanics. It's got to take into account, I kind of put these two items in here. I'm going to think of this as kind of a fundamental idea in quantum mechanics, that everything consists of fundamental particles, and that these fundamental particles all have what we call wave properties, or more specifically phase properties, and we'll see what that refers to. So electrons, protons, neutrons, neutrinos, photons can all be treated in a similar fashion. Now we've got the most experience, I would say right now, is with light. And so what this is saying is that how are we going to represent the phase of a particle? Now we've already looked at phases with light. And so let's take a look and see. Here, if we go back to, see, this takes us back to chapter 31. Here's an antenna. We have charges oscillating in the antenna, and those accelerating charges will radiate photons. And the photons can be represented in terms of their electric and magnetic fields. Now, this is has a wave look to it. Now, it's not. There's nothing waving here. What this actually represents is, as I look along the path of the photons as they travel outwards, there are locations where the accumulation of photons combine to give larger electric fields, and there are regions where the electric fields drop down. So this is the effect of, well, it's similar to this idea of phase, and that's why I thought it would be useful. And the textbook also refers to light as something where we have experience. So this is kind of a detailed picture. Back in chapter 31, we said if we accelerate charges back and forth in an antenna, we'll end up with a bunch of photons propagating out away from the antenna, and the direction of travel is this, and from one location to the next, we'll have different strengths, different magnitudes of their electric and magnetic fields based on what the acceleration of the charge was at that particular instant. So more photons or fewer photons being generated based on the acceleration of the electrons. And here's another picture. Now this is what we want to pick up. So what we said is, on this antenna, if I have charges moving back and forth, and we've used simple harmonic motion here, what we said is that the electric and magnetic fields propagate away from where they've been created. The photons are propagating away from that antenna, and that effect could be written as a sine or a cosine function. So of all the stuff on here, you're welcome to look at this in as much detail as you want, but this is the real takeaway. The takeaway is that we're going to have these photons represented by some kind of a sine or a cosine function, and we think of that as representing the phase. So for example, everyone's favorite radio station, radio photon transmitter, KQED FM, operates at a power of 110,000 watts. That would be 6.88 10 to the 23 EVs per second. Now, the photons that they use have a frequency of 88.5 megahertz. They have a wavelength of 3.39 meters. So I'm using all these formulas that we now have started making use of in quantum mechanics. And I can relate that to the energies of the photons. So the frequencies, the wavelengths are in terms of energy. And so if I'm given this information, I can solve for the energy of the photons. The photons that KQED radiates have an energy of 366 nano EV. They're in the radio part of the spectrum. They're pretty low energy photons. KQED is radiating 2 times 10 to the 30th photons per second. That's a really big number of photons that they're radiating. That's enough photons that you can put your radio antenna almost anywhere within a 50 kilometer range, 100 kilometer range, and you can pick up enough photons to reconstruct the sounds that were generated in that radio station. So if all the particles are going to be treated the same way as these photons, that would mean that we could take electrons, we could send them through some barriers, and we could create an interference pattern. Same as what we did with photons. If photons can do it, the electrons can do it. We just have to figure out what their wavelengths are. And we did that in the last chapter. So this is quantum mechanics here. So let's go back to this picture. Let's say we have electrons coming along here. We'll call this region A, and region B is over here on a screen. And between point A and point B, we've got some barriers set up. And what we want to ask is, how do we represent electrons or photons going from region A to region B? And we use what's called a wave function. Now the wave here, unfortunately, again, it's not like there's anything waving. There is this property that we call phase. Now, when we were looking at the photons, when we were looking at light, we were using sine and cosine functions. And sine and cosine functions are fairly familiar. What we need to introduce, if we're really going to do a correct version of quantum mechanics, is instead of sines and cosines, we're going to use complex exponentials. Now, if you've seen these in math classes, that's great. I'm guessing maybe you haven't, but the complex exponentials work very similarly to sine and cosine functions. In fact, what we'll show here is that complex exponentials are just a certain combination of a certain amount of cosine and a certain amount of sine. But they have nice features in that when you take derivatives of exponentials, you get the very same exponential back again. So this seems a little crazy. You don't have to know the details of these wave functions. But this is how typically a free particle, when a particle is just traveling from one location to the next, a free particle gets represented as some kind of what's called a normalization constant, a constant out front. And then there's a phase that has to do with how does the phase vary as it travels from one place to the next, and how does the phase vary as a function of time. What we find is that the wave number, now again, what we have looked at, what we want to make a comparison to, is this. Back in the early part of back in physics 3A, we looked at mechanical waves using sine and cosine functions. These were traveling waves. Little k, we've used little k too many times for too many things. The little k's here are what are called wave numbers. The omegas are what we call a radiance frequency, and that represents, if we go back one more, something that has a variation to it as a function of position and time. Now we want to use this to represent a particle propagating through space, an electron, a proton, a neutron, a neutrino, a photon can all be represented using these sines or cosines. And now we're saying there's a more refined mathematical representation, and that is in terms of a complex exponential. So if you look at the book, they're going to kind of go back and forth between using sines and cosines, and other times they use exponentials. Now, in quantum mechanics, once we recognize that this is the way, and this is the Greek letter psi. So I have to, when I was in college, my quantum mechanics professor, she liked to draw the psi's this way. She said, you just draw a line, and then you draw a squiggle through it, and that represents the wave function. Anyway, you can take a look at a more carefully drawn version of this in the textbook and go, oh, that's what it actually looks like. So this is the Greek letter psi, and the wave function tells us what the particle's properties are as a function of position and as a function of time. Now, the wave numbers that we have in here depend on the momentum, and the frequency, this is what we talked about in the previous chapter, depends on energy. And so what physicists realized is that if this is the generic way to represent a propagating particle, then a particle's energy could be thought of as an operator where we take a partial derivative with respect to time, multiply it by I h bar. Momentum can be taking partial derivatives with respect to x, multiplying by minus I h bar. This is a little weird, but this is what we think of as telling us about the energy and momentum of a particle, and here's why. If we've agreed that this is the way to represent a particle traveling from point A to point B, if I take what we've called the energy operator, and that's it right here. If I take a partial derivative with respect to t, that brings down a factor of negative I omega. If that gets multiplied by I h bar, negative I and I cancel out. Remember, I is the square root of negative 1. It's the imaginary number. And apparently, nature makes use of complex numbers, because in quantum mechanics, we end up using complex numbers all over the place in our formulas. So, kind of interesting. I mean, if you talk to a mathematician would say complex numbers are great, they have a wonderful set of properties to them. Numbers are incomplete if you only use the real numbers. You got to bring in the imaginary numbers to make the system complete. And nature seems to agree. Nature appears to make use of complex numbers because that's what we end up using in our formulas to represent what's going on. So when we take the energy operator and operate on this wave function that represents our electron or proton, we get a factor of h bar omega. H bar omega is the energy of that particle. So doing a series of operations gives us the energy times the wave function back. Momentum works the very same way, except momentum involves taking derivatives with respect to x, y, or z, depending on which component of momentum we're looking at. And so this is, I mean, it's a lot to kind of throw out there all as one package, but what we're trying to do is come up with a consistent set of formulas where this represents a particle propagating along some direction, and this is how we figure out what its energy is, and this is how we figure out what its momentum. Now, often what students will say is, well, it's all just circular, and the response to that is exactly. What circularity means is that everything is consistent. Now, whether or not this describes nature comes down to running experiments and doing observations. But all of the mathematics that we use throughout physics, it's consistent. It's mathematically consistent. And then the question becomes, does it represent nature or not? And for that, we go out and we do observations. And quantum mechanics now has been around, you know, this mathematical formalism has been about 100 years, and it works. It works just really, really well. Seems crazy, but this is apparently how nature operates. So let's take a look at a couple of other examples using these formulas. So what we could do is this. Let's go back to relativity. Now remember, the fundamental formula in relativity said that energy squared for a particle is equal to momentum squared plus its mass squared. Now, if I replace E with the energy operator and P with the momentum, there it is, operator, then the energy operator creates for us, and the momentum operators create for us what we call a differential equation. Now, differential equations are not a prerequisite for this course, so this is just informational for you guys. We start with a statement, a formula from relativity in terms of energy and momentum. We replace that with the energy and momentum operators, and what we have now is what's called a differential equation. And again, if it's not making sense and it's not useful, it's not helping to understand, don't worry. But this formula, if we apply it for photons, this formula could be used to represent the propagation of a photon or an electron. The solutions to this formula are sines and cosines and exponentials. So this is actually showing us where the wave functions are coming from. Now, the photon example, we would need to set the mass equal to 0. When we do that, the formula we end up with, if you go back to chapter 31, was a formula that was introduced for the Maxwell's wave equation. This was a formula that Maxwell derived back in the mid to later 1800s. That was a little bit of quantum mechanics that Maxwell stumbled onto. So the propagation of electromagnetic fields, the formula used to represent that is a quantum mechanical formula. Okay, so now we could work from this relativistic equation, but it turns out that for convenience, often what we do instead of using relativity, we go back and use what's called the Schrodinger equation. Now, if you've taken chemistry, you've probably heard of the Schrodinger equation and maybe even seen some simple examples of it. So that's what we're looking at here. Now, the Schrodinger equation says that the energy of a particle is the combination of its kinetic and potential energies. It's not relativistic. It does not include the mass energy of the particle. So an MC squared term is missing. But if we go back to classical physics, kinetic energy is given by 1/2 mv squared. That can be rewritten as momentum squared over 2m. So this energy formula from classical physics becomes, in terms of operators, becomes the energy operator is equal to 1/2m. That's from writing down the kinetic energy. This is our kinetic energy here, written in terms of momentum, and then the potential energy. So the differential equation looks like this, and if we substitute in a wave function, it looks like that. So this is what the Schrodinger equation looks like. And it all comes from these definitions of energy and momentum operators, and that comes from the recognition that the generic mathematical representation of a particle is this. That is the wave function for a particle just traveling through space on its own. Okay, let's take a look at some stuff that we're actually, let's look at some more quantum mechanics here, I guess. So if the wave function is represented by this, the probability distribution, the probability of where a particle is located. Now this is a little strange too, because in classical physics we're used to thinking there's just this trajectory and the particle just follows a certain trajectory. In quantum mechanics that's not the case. In quantum mechanics the particle is represented, instead of existing at one point, as existing at a range of possible locations. And so to calculate the probability of the particle being at a certain location at a certain time, we square the wave function. Now, since the wave functions are complex, they have factors of I, where I is the square root of -1, we do what's called modulus squared. So that means that we take the wave function, and we take the wave function itself, that we've written up there, and we multiply it by its complex conjugate. So e to the ikx becomes e to the minus ikx, and e to the minus I omega t becomes e to the I omega t. Multiplying these together gives us 1. Okay, so if you have looked at complex numbers and exponentials of complex numbers, these are properties that you'll discover. So, a particle represented by this wave function has a definite momentum, given by h bar times the wave number, definite energy, h bar times omega, the frequency, but it's equally likely to be at any location. So this wave function, we use this a lot, but it has some nice features of definite energy and definite momentum, but it has a downside, and that is that it's predicting a particle is located everywhere. Now that doesn't work well, so instead of using that to represent the particles, often what we end up using is a modification where the particle is bunched into a region, and we represent this region as having a distance of delta x. So if I've got a photon or an electron and it's been bunched into a region within a certain distance, and we use this as a wave function and square it, what we find is that the range of possible locations requires that the particle also have a range of possible momentum values. If the particle has just one definite momentum, that requires the particle to be equally likely to be found at any location. So we have to reach a compromise. And the compromise is, okay, we're going to say the particle is being found within a region the size of delta x around some central x value, and that it's got a range of possible momentum or wave numbers around a central value. Now there's a bunch of math here that I'm not so interested in, but what we can show is that these two properties are related in a way where delta x times delta p is equal to h bar. Some of you may have even seen this. This is referred to as the Heisenberg uncertainty principle. So what it says is, when we sit down and we run through all the mathematics describing how particles get from point A to point B, we run into kind of a, well, it turns out not to be a contradiction, but it turns out to be something non-intuitive. And that is that, and it's, okay, I think there are different interpretations of this. This one is saying that there's a limit to measurement. But notice they follow up with, not because of the instruments, but in terms of the properties of the particle itself. So this is not, so I don't want to call it limits to measurement. I want to say that particles don't exist at just one location. Particles have a possible range. They have many possibilities open to them. So I've never cared for the Heisenberg uncertainty name. Uncertainty sounds like we don't know what we're doing. I prefer the Heisenberg possibility principle, right? Because the particle can be found in many possible locations, not just one, but in many possible locations, and that the particle doesn't have just one value of momentum. It could have many possible values for its momentum. Until we go in and do a definite measurement, we have to allow for the possibility that the particle could be located in many different locations and have many different values of momentum. Okay, so it's the Heisenberg possibility principle. And mathematically it looks like this, and we'll look at a couple of examples. These are some of the formulas that get used. These are, if you've taken statistics, these are just normal distributions. And it says this, it says that if I want to represent a particle as being at a very narrow region of space, maybe this blue distribution, I have to allow for a wide range of momentum. Or, vice versa, if I want to have a particle with a very definite momentum, it's got to have a wide range of possible locations. What can't happen is, there's no mathematical way that we can represent the particles as being both at a very small region, a very confined region of space, and at the same time have a very definite momentum. Those two things they're not consistent with each other. There's always a range of possible locations or momentum. Now there's a similar, this might look like the very same slide, but this is in terms of energy and time. So the same way that momentum and position are what are called conjugate variables. If we try and narrow the position, then the range of possible momentum gets bigger, and vice versa. If we try and narrow the range of energies, limiting the particle to have a very definite energy, then it has to exist at all possible times. Okay, so that's how these work. So let's say that we have an electron. An electron's moving in a straight line. It has traveling at a speed of 1.1 10 to the 6 meters per second, and it's been measured to a precision of 0.1%. What would be, okay, so this is the precision on the velocity. What would be its position then? How much of a range of possible values? So again, what we've got is a particle all by itself. This is representing a range of possible locations. It's not just at one location, it's kind of a blob of different locations spreading through space. And the wave function here would be definite momentum and definite energy. So what we want to do is we want to use the Heisenberg uncertainty formula. I'm going to start off by saying that the momentum, m times v, works out to be 1 times 10 to the minus 24 Newton seconds. I'm just using standard units here. Now they said that this momentum is uncertain. The velocity is uncertain, therefore the momentum is uncertain, to plus or minus 0.1%. That would say that the particle has a momentum, kind of a central average value of 1.00 10 to the minus 24, but it's also got this uncertainty range. It could be higher or lower by this amount. Now I took the Newton seconds, I multiplied that by c, and that says that the range of possible values of momentum, the momentum of this particle, first of all, works out to be 1875 eV, and the range would be plus or minus 1.875. So that's a range of possible values. Now what I can do is I can solve for delta x. Delta x then is going to be given by h bar over delta p. So here it is. So here is our Heisenberg possibility formula. I'm going to set this to be an equal sign just to simplify the calculations here. And I'm going to solve for delta x. So the plus or minus on the delta x works out to be 105 nanometers. So what that's saying is, for the electron that we're representing, the momentum has this uncertainty of about 1 part in 1,000, and that says that the position then is only well known to within 100 nanometers. So a mathematical representation of this particle predicts that there's a range of locations where this electron could be found. And when we do experiments, that's what we find. When we look at how are electrons distributed in atoms or molecules, they are consistent with this Heisenberg principle. Now, So what that's saying is, here's a wave function we would like to use for the electron. Its momentum is 1875 eV plus or minus 2 eV. The location is equal to wherever it is, plus or minus 105 nanometers. All right. And I think that's enough. We've solved the part that they've asked us to take a look at. Now the Heisenberg uncertainty stuff, it's kind of interesting, but it's not the most important part of the chapter for us. They have us come back and do another one of these with a baseball. So I'm going to plug some numbers into this. Here is the baseball. So again, the principle we're looking at here is that the range of possible momentum for this baseball does not have one definite momentum. There's a range of possible values times the range of possible locations is going to be approximately given by h bar. If I solve for delta x, then I'm looking for h bar over delta p. H bar is given by 1.055, 10 to the minus 34 joule seconds. I just need to find out the range of momentum. Now, the mass of the baseball is given as 150 grams. The velocity is 42 meters per second. I'm going to convert this into kilograms. And I find out the momentum of this baseball. The momentum itself, kind of the central value, is 6.30 Newton seconds. But that the delta m, they're saying that there's an uncertainty in the velocity of plus or minus 1 meter per second. So that was given in the problem. It's 42 plus or minus 1. And so I'm going to represent that. This is 42 plus or minus 1. The plus or minus, I'm going to plug into here, 1 meter per second. And that says the momentum then is 6.3 plus or minus 0.15. Now in classical physics, we would say, oh, that's just an uncertainty in the measurements. In quantum mechanics, what we're saying is it's a fundamental property of the object itself. It really does not have a definite, fixed, just one value of momentum. So plugging into the formula here gives the uncertainty in position of a baseball that's been thrown here, 10 to the minus 34 meters. So again, it's one of those examples where we really don't have, that is so tiny, we really don't have a way to go in and find out, do baseballs follow quantum mechanics the same way that electrons do? Similarly, I'm going to run through this example really fast. Back in 1974, there was a new particle discovered in a particle accelerator. Very exciting. It was the charm quark. It was a charmed anti-charmed quark-anti-quark pair. People were very excited. It was simultaneously discovered on the east coast of Brookhaven and on the west coast right here at the Stanford Linear Accelerator Center. When I was in graduate school, not 1974, but about 20 years later, the controversy was still going on as to who actually discovered this particle. Clearly Stanford did, because that's where I did my graduate research, the Linear Accelerator Center. Anyway, Brookhaven and Stanford have argued back and forth now for, what, 50 years or something. Brookhaven calls it the J, the Stanford people called it the psi. Anyway, what we're interested in is this particle has not one definite mass. This is kind of an interesting feature of short-lived particles. This particle lives a very short amount of time. It's not stable. It's not anywhere near stable. In fact, it lives for such a short amount of time, we don't have a way to measure that. So instead, we use the Heisenberg possibility formula, and what we say is we measure the energy of this particle. Now, the particle's energy is just its mass. And so we run a set of experiments, and we find that this particle can be generated most often at a mass of 3100 MeV, but sometimes the mass can be higher and sometimes lower. So if I find a particle whose mass is uncertain, there's a range of possible mass values, that's an indication that it has a very short lifetime. And so we can use the Heisenberg formula. and say that its lifetime, delta t, is given by h bar over the range of possible energies. And what they found for this particle is it had a range, what's called a width. It's called a width because of this graph that's done in terms of how many of these do we actually see when we run the experiment as we vary the energy. And so that's called the width, and that's delta E. Delta E was measured to be 63,000 EV, and so that gives us a lifetime of 10 to the minus 20 seconds. So if you've ever wondered, wow, how do they measure those short lifetimes? This is it. They actually measure the energy width, the mass of the particle, and then use the uncertainty principle. All right, so this is our philosophy slide. Classical physics, Newtonian mechanics, is what we call deterministic. If you start with a certain set of conditions, if you throw something, it always follows the same trajectory if you throw it at the same speed under exactly the same conditions. Quantum mechanics says no. There are actually many possible paths. Now you might think, well, is quantum mechanics just completely random then? And quantum mechanics is not random. The universe isn't just completely anything happens. Quantum mechanics predicts probabilities. So quantum mechanics predicts very definite probabilities of each of the possible outcomes. And so you might say, well, how could nature be predictable if it's based on probabilities? And the answer to that would be, have you ever been to Las Vegas? So Las Vegas and other places where people are, cities that live off of probability, they can do really well. When people walk into the casinos, they don't know who's going to win and who's going to lose, but they know that if you run the experiment enough times, there's a probability of different outcomes, and they know exactly what the probabilities are. And they know that the probabilities, are designed to be in the favor of the owners of the casinos. So yeah, you can have a deterministic or a probabilistic nature or probabilistic universe and have a consistency of outcome if things are being run many, many times. And that's how quantum mechanics works. Now we're getting back to these wave functions. So again, the textbook is kind of using both. Sometimes they use sines and cosines. That's what they've done here. We've talked about this. The little k here is the wave number, and it's related to the momentum of the particle. Here is what the Schrödinger equation is based on, is the idea that this is kinetic energy written in terms of wave numbers, and kinetic energy plus potential energies equals something we call total energy, but it's not the total energy from relativity. It's the classical total energy. That gets rewritten as Schrödinger's equation. Okay, now this is mathematics again. What we can do is we can take the wave, that's what the wave function looks like. So you guys have seen my representations of this. But this is actually what the symbol psi, it was here too. So this is actually what psi is supposed to look like. I apologize for my handwriting. This is what's called normalization. So if I take the wave function, that's a probability density. If I integrate over all possible locations, that has to add up to be 1. So let's take a look at, let's break the wave function apart now. Here is the wave function, which tells, where are the possible locations of the particle and what are the possible times at which the particle will be there. That can be broken up into space, a spatial factor, and a time factor in many situations. And whenever that's possible, the time factor, this function over here that represents how time is varying, we can continue to use negative I omega t. That's what we were using before. Here they've written it as energy over h bar. So that time factor remains the same, and what we can do is we can factor out the spatial portions. So the spatial portions, the x portions here. Okay, let's move on from this. Here we go. So what they're looking at in this example is they're looking at what we're going to call free electrons. Again, it's a particle just going from point A to point B. It's not running into anything else. It's just out on its own. And let's come up with a wave function representing this electron. Now what they tell us about this electron is that it has an energy of 6.3 eV, and it's in free space. There are no potential energies involved. What would the wavelength be, and how would we write the wave function? Okay, so first of all, let's be clear. We've studied relativity. The 6.3 eV they're talking about, that's only the kinetic energy of the electron. So the mass energy of the electron is still 511,000 eV. So we want to keep track of both of those. Now, the generic wave function that we're working from, we could do this in sines and cosines, but we could also do this as complex exponentials. Now, what that tells me is to represent this electron, they are telling us this electron has a definite energy and it has a definite momentum. So, now, in the Schrodinger equation, the energy is the kinetic energy, and so the energy is given by p squared over 2m. But that energy actually, in relativity, is going to include the mass energy of the electron. So what I got to do is this. The frequency of this electron, I'm trying to find two quantities here. I'm trying to come up with omega and k. Once I've determined omega and k, I'm done. I know how to write down the wave function for this electron. Now, the omega is given by the energy over h bar, and since we've studied relativity, we know in addition to the kinetic energy, we've got to include the mass energy. In fact, mc squared totally dominates. This is even, this is pretty insignificant. So the frequency here is going to be given by 7.75, 10 to the 20th radians per second. Okay, now what about the momentum? For momentum, because the kinetic energy is so low compared with mc squared, we don't have to use relativity here. Instead, we can use classical formulas where the momentum is given by 2mk to the 1/2. Now, to make that a pc, I can put in a factor of c squared. I put those in, I put in the kinetic energy. I now have a value for pc for this electron. So this electron has an energy that's dominated by its mass, and it has a momentum of 50.4 eV. Now, I can figure a wavelength is going to be hc over pc. That was my reason for calculating pc instead of p by itself. I'm going to calculate pc, and that works out to be 24.6 nanometers, and I got to use my hc shortcut. So putting all the numbers in, I get 24.6 nanometers. The wave number is given by 2 pi over the wavelength. So, initially we said we needed to find little k, the wave number, and the frequency. The wave number is 2.55, 10 to the 8th radians per meter. The frequency is 7.75, 10 to the 20th radians per second. The wavelength of this electron is 24.6 nanometers, is how that all comes together. Okay, and again, we've gone through this before, so we can move quickly on some of these. Here is what the wave function looks like as a function of x. So here is either a sine function or a cosine, or our favorite, my favorite, using the exponentials. This would be a particle that's located everywhere. If we want to confine the particle to a smaller region, then we can use what's called a wave packet, and it will be packed into a smaller region. So just something to be aware of. Okay, now we're going to get into something that maybe is the most important part of the course, of the chapter, not the entire course. The most important part of this chapter for us is asking, okay, can I use all these wave functions and wave equations that we've talked about, can I use the Schrodinger equation to predict the properties of a particle, maybe it's an electron, that is confined to a certain region? Now, by confined to a region, what they're saying is imagine the potential energy goes really high and that the electron can't get out. What does that mean? Well, if it's an electron in an atom or a molecule, it just means the atom or the molecule is holding on to it, and there's no easy way to leave. Now for this, we actually can use sines and cosines. Sines and cosines turn out to be the best solutions. We find out that there's an energy formula given by n squared over h squared 8ml squared, where n is equal to 1, 2, 3, and let's see what that solution looks like. What we find is, if we're going to use the Schrodinger equation and represent the electron inside a region, now again, what I'm going to suggest you think about this as, it's an electron, and it's inside an atom or a molecule, and because of the electromagnetic force, it is confined to within a certain range. Well, that tells us that the wave function then needs to have this phase property to it, but the wave function also needs to go to 0 at the edges. Quantum mechanics says that there's a region where the potential energy sharply rises to a large value that the wave function itself has to cut off very rapidly. So these are the possible sine functions that represent the wave function of the electron in that region. Now what's interesting here is, because now we're actually dealing with sine functions, when we calculate the probabilities will show definite variations from one location to the next. So if you've got an electron that's confined to a certain region inside a hydrogen atom, for example, there's going to be a region where it's more likely to be, but in the excited states there could actually be multiple regions of probability with negligible probability between them. So this is an interesting prediction of quantum mechanics that we see plays out in chemistry. So basically what we're looking at here, much of what we're looking at in this chapter, is kind of the fundamental quantum physics foundation for chemistry, for chemical bonds. How do chemical bonds form? Well, electrons end up being in different patterns. And those patterns can be calculated by, first of all, solving for the wave functions, and then squaring the wave functions to find out the probability distribution of the electron. Now, not only does this apply to electrons inside atoms, it applies to protons and neutrons inside the nucleus. Protons and neutrons inside the nucleus also are represented by wave functions. They have wavelengths and frequencies along with their energies and momentum. And that means that the probability distribution are going to have higher probability and lower probability patterns to them. So this is a nice side-by-side comparison. Here is the kinetic energy of the different possible states. Now, this is not the hydrogen atom formula. This is a very rough, one-dimensional approximation using the Schrodinger equation. So we're not at the three-dimensional hydrogen yet. So we can't do a direct comparison with the Bohr formula for energy, for example. So again, let's think about this. So let's say that there's an electron, it's confined to a region. Here are what the possible wave functions look like. If I square those, these become probabilities. So it says that in the lowest state, the probability is bunched in the center. But if the electron goes into the excited quantum state, there are going to be actually two regions of high probability, but there's going to be a region of very low probability between that. So squaring the wave function gives the probability, and it turns out for a particle confined to a region, now it's just a one-dimensional example right now, those are given by sine functions. So this is the equation, this is the Schrodinger equation that we start from, and these are what are called boundary conditions. So not only does the wave function have to meet this requirement, but at the edges the wave function has to go to 0. It turns out that the sine functions are what solve for this particular situation. Okay. So that's kind of this is the mathematics behind all of that. And so if we do follow the Schrodinger equation, the Schrodinger equation has us taking a couple of derivatives. And so the Schrodinger equation, if we go back, oh, it's right here. So the Schrodinger equation says that we got to take a couple derivatives of the wave function. When we take a couple derivatives of our wave function, oh, here's one derivative. Here's the wave function. Here is taking one derivative. Here is taking two. I take two derivatives, plug it back into here. Following this through, and then canceling out the wave function on both sides leads to the kinetic energy of the different possible quantum states. So the wave functions have this formula representing the wave function, and these are the energies of the different states. So we're getting to where we want to take a break here. And yeah, let's go ahead and take a break, because this example is so important for us. We'll come back. Let's take a break now. We'll come back in 10 minutes or so, and we'll take a look at the rest of the chapter.